At the end of the last video, I got the ALU to add a couple of things together with the correct timing that I was looking for, and quickly declared victory and ended the video. Well, that ended up being an hour-long video, and I don't want to go down that path again. So I'm going to take a step back, and rather than trying to get the goals that I set out for at the start of each video accomplished, I'm going to work against those goals. But once I reach about 25 minutes, I want to try to cut that video at that point, and anything that's not working will punt down to the next video. Producing an hour-long video for me is very challenging to do. I'm sure it's very challenging to watch as well. So in this video, what I had planned for, and I'll stick them up in the corner there, I want to address the two known ALU adder issues. One I commented on, which is the lazy add or lazy bit on the ALU itself. The second is, and I didn't comment on this, the Z flag is not actually working properly. So I want to get both of those straightened out. And anything else that I happen to uncover along the way there. Then I want to make sure that I get some ALU related LEDs put up. I only have the result that's there and the flags that are there, so I want to clean that up and make sure that I'm actually getting good values showing up for the ALU input and the control signals. So I will work on getting those done as well and get that taken care of in this video. And it may end up being all I have time for. So once I reach about 25 minutes or so, then we'll take what's not done and make it the top priority for the next video. Now, time permitting, I do want to go through the ALU adder tests that I have. There's 24 of them, and so there's going to be quite a sequence related to those. And then I need to do some additional conditional execution testing now that I have all my flags available to me. And so I will work on getting those. I may or may not be able to get to them in this video. We'll have to see how this all works out. All right, enough of me rambling on this. Let's get right into this.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Okay, most of what I'm going to be looking at here is going to be down here in this corner. I'm going to start with the ALU adder lazy bit, as I'm calling it. And so the challenge is that the bit, and I see it in the results that end up getting latched, and the results here, there's one bit or multiple bits that aren't actually showing up quickly enough. Now, what could be causing that? Well, I know that the problem is not on these line driver ICs, or at least not the output of the line driver ICs, because not only do I have the problem here, but I have the problem exhibited here as well. I don't believe it's going to be related to the inputs. And the reason I say it's not related to the inputs is I don't think there's anything here in these line drivers which are going to cause an issue here. Now, it could be these line drivers over here, or it could be related to the adder itself. And so I need to try to discern where this problem actually comes into play. And it actually could be potentially here in the inputs as well. So something in the inputs is dragging something or making it lag behind. Okay. I have the yellow trace hooked up to the bit in question. I have the blue trace hooked up to bit 0. Let me show you what I think I'm seeing here. So I'm reset. My trigger is on the bit 0 in the falling edge. So this is different than I was expecting to see. As the bit 0 falls, the bit in question rises. Now, what does that mean over here? Well, it means that these line driver ICs are actually properly conditioning that output. It's a nice sharp edge. Let me go to the input side and let's see what that looks like. Same setup over here. The yellow trace is on the bit in question. The blue trace is on bit 0. And so my transition from high to low on bit 0 is my trigger. I'm reset. And that's interesting. I am not sure where that spike is coming from. Well, I think I need to start looking at the inputs and make sure that the inputs coming into the ALU are accurate. Let me start with ALUA. It's the next one down here. So it's going to be what's coming off this line driver here. Okay, Once again, still the same setup. The yellow trace is the bit in question. The blue trace is bit 0. And that, I believe, looks good. R1 would have had that bit clear, so the yellow trace would have been 0. R1 would also have had the least significant bit clear. So I'm measuring the symptom, but I'm not measuring the problem, because the bit in question remained low, which I see here, whereas bit 0 climbed high, which is what I see here. So I'm seeing the symptom of this problem, not the actual problem itself. Let me try ALUB. Well, I may have measured this incorrectly. I probably need to keep the bit 0 to be tied to the actual output. So let me try that again real quick, just to make sure that I didn't do something silly. Yeah, I'm seeing a spike on this bit in question, which is interesting. Okay, let's try that on ALUB just for giggles. And again, I am tied to the result out here, and that looks reasonable. Now, there is going to be a period of time when R1 has latched the result and is still asserting out onto ALU Bus A, which would indeed create that symptom that we saw over here. But that should not impact the amount of time it takes this to calculate the first result. I'm hesitating on all of this because A, I'm not sure that I totally understand it, but B, I'm not totally convinced I don't have a bad IC here in the adder. And I think what I'm going to do is make an attempt to replace that IC, hopefully without making a complete mess of everything. Let me make sure that I've also got my capacitor hooked up to the right pins as well, because that could have an impact as well. It could make things look lazy. I'm going to pull up a Venn diagram here. Bit 1 on this one is not used. The result bit 0 is bit 2 down here. Result bit 1 is bit 3 here. Result bit 2 is bit 4 here. Result bit 3 is bit 1 here. Result bit 4 is bit 2 here, and that some bit happens to be right next to VCC, which makes me wonder if I have the capacitor hooked up correctly. I should, and it looks like I do. But that would have been this line right here. Let's try pulling the capacitor and see if that makes a difference in behavior. I'm going to go back to measuring up here off the ALU result. I already saw the problem again. Yeah. See, even here I've got this little jog in the signal. All right, I'm going to replace that IC. Let me get that done. We'll come back and retest. Okay, that was a little fun to try to dig out. Not my favorite thing there, but I'm powered back on. And let's see what we end up with here. Yep, I saw it over here. Next option might be a bad wire. Might be something on the ALU A or B bus that is acting like a capacitor. I'm going to have to think on this a little bit before I make my next step here. Okay, you'll notice I have R1 and R2 registers pulled out. And that's because I decided I would try testing ahead of these line drivers, which are really helping to pull down the signals. ALUB, it turns out that that suspect signal was actually coming high late. So that means that there's nothing wrong with the ALU here. It's my input signals. So looking at the R1 register, I did happen to find, just looking in my own eyes, one pin that's literally floating. It's up in the air, so I've got to get that dealt with. Looking at the R2 register, This one is enough of a mess. I think it's the first one I soldered up. So long story short, I need to get the microscope out and take a look at this under the microscope and figure out exactly what is wrong and what I need to fix here. These are the line drivers for ALUB. These are the line drivers for ALUA. And those have not been exercised on any of these boards yet. Okay, I need to move the build out of the way in order to get the microscope out and actually set it up here. Let me do that. I'll be right back and we'll get some close-up details here. Okay, this is the R1 register, a very out of focus R1 register. But... And can you see it? I've actually managed to bend the pin pretty darn good in my probing around, but that is not attached to the pad at all. Now, but right next to it, that one looks suspect as well. As a matter of fact, they all look pretty bad. This is ALUA, and those are the lower 8 bits. Now, the other thing to consider is if I look at the back of that pin, I don't see any solder on the back side of that. I've obviously got quite the mess going on here. There's very little solder back there as well. So I'm going to need a whole ton of flux and a whole ton of patience, and I might even have to pull this particular, nope, not that one. I might have to pull this IC just to get the pins straightened back out and aligned properly, which might mean that I just chuck the IC and this is ALUA for register 1 over here, and it doesn't look horrible. There's one pin here that looks like it might have a little bit too much solder on it, and that ground pin may be floating as well. This is this end pin right here. But once again on this end, this just does not look like a quality solder job at all. There's nothing on the back of the pins at all. Nothing managed to make it around. Now these were probably the first 2 that I soldered. If I look at these pins, these don't look really brilliant either. All right, so that's R1. R2 doesn't look quite as bad. Again, I've got situations like this where I've got solder that's up near the top of the pin but not down near the bottom. Again, doesn't look horrible. This is ALUA up here. So this one actually looks like it is in better shape than the other one because all of these look like they're properly soldered down. That's got a little bit of a tail on it here. Again, if I look at the end, that actually looks like I bridged that particular joint to itself. The pin itself back here looks like it's got no solder on. And again, there's very little solder back behind the leg. Almost no solder back behind the leg. So I'm going to warm up the soldering iron and see what I can't do to try to make this look better. I'm going to need a whole bunch of flux and a whole bunch of patience. Those actually look better. I at least look like I managed to get solder back behind the back side of each IC, or each pin, I should say. Okay, let me try the inputs, see if we can get those settled. Alright. Now let's deal with the bent pin here. And to do that, I'm going to use some solder wick, but this is massive. So what I'm going to do is I'm going to take my cutters and I'm actually going to cut this in half. Bend this appropriately. Put a crazy amount of flux on this. And I'm going to stack the deck in my favor by preloading my solder iron with solder so that I can actually get this pulling up, hopefully. That actually looks reasonably clean. I wonder if I can bend that. See if I've got solder underneath that. Well, let me get a pair of tweezers. That's this one I need to bend. Okay, I'm gonna have to desolder the chip. Okay, I have it. Now I just need to clean up. Okay, that's one side done. R1 has been cleaned up, and I want to drop this in here. R2 has also been cleaned up. So there we go. And, well, let's just go straight into a test. Okay, I should be able to just observe what's going on here in the results register, ALU result, and see what's really going on there. That was instant. Now the extra little flash there again is the result of having the ALU asserting, ALU Bus A and ALU Bus B asserting as things are being latched. So I'm good with that. I'm gonna call that fixed, or at least the lazy bit fixed. And now we just need to get into why everything is reporting 0. Let me demonstrate that problem. So I've got my 0 flag is set. And as that gets latched, it doesn't change the 0 flag. All right, so that's next up. Now, the ALU bus here is also coming over here to these 74 HCT 540s. These are line driver inverters. So every single signal here coming in will be inverted coming out. So I should have all highs here. Now, these are 8-way NAND ICs here. So the output here should be something other than floating. And that's floating. So not connected, high, high. Yeah, that's floating. That's low. That's floating. Why is that floating? That's high. That's low. All right, let me pull this. Now it's low. And now that's floating. So there's something going on with this 74 LS08, I believe it is. 02. So that's a NAND. Sorry, that's a NOR gate. Yeah, question is do I have that hooked up right? And I probably do not. I need to pull up a pin diagram because the 74 LS02s have a funky pinout. I don't have one handy. I gotta go dig one up. Okay, I'll tuck that up into the corner for you. I am using up here this top left gate, and sure enough, it appears that I have the output of this 8-way NAND gate tied into the output of the NOR gate, and I am picking up as one of the inputs the carry flag. So I need, and it's underneath all of these lines up here. So I need to get that sorted here. This will be relatively easy to move, or remove, I should say. This one's going to be much tougher to get to and relocate. So let me see if I can pull this out here. Okay, a couple of small little jumpers here. One goes from this output signal here over to the proper input on that NOR gate. The other one is, now where was that hooked up? I lost track of that. That would probably have been here. It needs to come over to that spot right there. So the problem is that the NOR gates are wired up backwards from every other gate, logic gate that is produced. And that's annoying. All right, resetting. So now that's showing low, that's showing low, and my 0 flag should be high now, which it is. Which means that when it's latched, this 0 flag LED will come on. All right, so let's give that a quick test here. And there is, nope, that's not it yet. There's my add. My result is 0, so the 0 flag should come on. That's good, it did. Set carry, carry flag comes on. So now I've got my alternating bit pattern, which goes into R1, alternating bit pattern, which will go into R2. I add these two together and it should be all Fs, so my zero flag should turn off. My carry flag should turn off. Okay, that's asserting out on there. This will be the instruction that does it. Well, my zero flag did turn off properly, but my carry flag did not. All right, so where's my carry flag? My carry flag's coming out of the adder down here. And this should be my carry input, which is low, carry output, which is low. Both of those should come up here to this one. So which one's which here? Okay, so there's my carry output. My carry output should be coming up to this signal here. And that is accurately low. So here's the pin diagram for the 74LS74. This pin here, pin 2, should be my carry, which is accurate. So my output, and that's already latched, and I've got a no-op in the code there. So that's already performed its latch operation. So this pin here, did it clock? Almost like it didn't clock it. Let's reset and try that again. Okay, assert, and it did clock it, but yet that's high somehow. Let's try resetting that. I want to track what happens with that pin. That was the set carry. That never changed. All right, looks like I need to get the scope out and check the sequence of those signals. I'm set up for, let's set it for a single trigger on the rising edge on channel 1, so I want that to be my clock signal. Let me quickly pull up the pin diagram just so I know what I'm hooking into here. My clock is on pin 3. And then the other signal I want to be the data signal. That's going to be pin 2. Okay, trying to fit that down in there. There we go. All right, I think I'm good there. Okay, so if I reset now, okay, so my yellow trace is my latch, and it's latching while the value is high. I think I need a wider time frame for that. Let's try that again. It's not going anywhere other than high. Let's see here. That was supposed to be carry. Oh, I might have been playing with the zero flag. That could be why it's not doing what I thought. So let's try this again. Reset. Okay, it's latching while it's low. That's good. We'll keep going. And this is latching during a transition. So how close do we need to get on this? Looks like I need a slight delay in the latch. So my latch is happening prior to the signal change. So what I need to do is I need to trace that signal back down over in the control logic and see if I can shape that any better. That signal in question is coming off of control ROM 8 and it's bit 4. That bit is over here, so that signal is NANDed with the clock, such that I have a normally high signal. During the first half of the clock cycle, that signal comes low, and then on the falling edge of the clock, effectively, is when that gets latched. What I think I really want to have happen is I want that signal to be congruent with the ALU output latch, which is over here. So for a quick test, what I think I'm going to do is I'm going to take this result signal. No, I'm going to do it differently. I'm going to reach up here and take an inverted version of the signal that drives this ALU result latch, and I'm going to replace, if I can get to it in here, I'm going to replace the clock signal that this is NANDed with. And this way, my carry flag is captured at the same time the output off the ALU is captured, which seems like the reasonably correct time to do that. If this works, I will come back around and address this logic over here such that it's all congruent and I'm taking the correct signal for all of this. All right, let me reset. We'll give this a shot. That did not do what I think it should. That will cause a latch when I don't want it to. That's properly going to latch there, which is appropriate. All right, what if I move it earlier a little bit? So my carry is still latching before it goes low. So I need to delay that latch still. I'm going the wrong way by making it earlier. I need to make it later. See if that's going to give me what I want. I'm latching just after that change of state now. Let's move this back to... Let's move it back one and see how that works out. Yeah, that still latches before the change. Alright, let's try with the inverted clock. That's the spike clock. Let's try with the inverted clock. Let's try this a different way. Let's set this up to be the falling edge of channel 2. Now channel 2 is my actual carry flag as it's changing. Okay, so now my clock, as I want to drive that, I want to look and see which one makes the most sense compared to when that signal is actually dropping. And let's start with the actual clock here. So let me reset. So I'm falling, but I'm falling after the rising edge of that clock. All right, now let's go to the most delayed clock I've got. Now I need to take it from before the last inverter. Yeah, so my falling edge of that clock is still prior to the change in state. I want to check now that signal. This is the ALU output latch. Do I need more delay back up there? I need to think on this a little bit. Well, I hate to keep this unresolved, but I've reached the limit that I committed to at the beginning of the video. So I'm struggling here a little bit with the carry flag and the timing. Something's not right here. That should be calculating and able to be latched at the same time the rest of the output is done and ready to be latched. And I got that worked out in the last video. So there is something that's not quite right here, and I've got to get my head around that, but we'll talk about that in the next video. At the same time, I want to make sure that I get, at some point here, LEDs to show the inputs and the control signals, and so just to make it a little bit easier for debugging. Now, I've real tight on space over there, so I'm not exactly sure how I'm going to be able to pull all that together, but I want to make an effort to get that done so that I can actually use that information for debugging. We'll see you soon.